Hello everyone and welcome to another video. Today's lesson is going to be about fluids in motion, and this is the second part to that lesson. After watching this video, you should be able to understand and apply Archimedes' principle, be able to calculate buoyant force, and then understand and apply Bernoulli's principle. So let's get right into it. Before we talk about any of those things, I've been kind of discussing a concept called density, and I want to just go over that real quickly just to make sure we're all clear what density is. Density is a ratio of mass to volume. So for instance, if I have, say, 1 cubic centimeter of marshmallows compared to 1 cubic centimeter of lead, which is going to be more dense? Well, I think you always say, well, the lead will feel more dense in my hands, and it's just because there's more stuff packed into that cubic centimeter of lead compared to, say, marshmallows. So just a real quick density side note here. In physics, we use this unit called rho, which is RHO, and that's the symbol for density, and to me it looks like a P, but it's actually not. The symbol is rho, and it's mass over volume. So let's do a quick density problem here. A single kilogram of water fills a cube with a length of 0.1 meters. What is the density of water? Okay, so remember, density is a ratio of mass to volume, so it's going to be rho equals m over v. And my mass is 1 kilogram, so that's just going to go on top, divided by, it says that I have a cube, and the definition of a cube is that all sides are equal, and one side is 0.1 meters, so all the sides are going to be 0.1 meter, and if you multiply that by 0.1 3 times, that would get you the volume of this cube, okay, because volume is length times width times height. All right, so 1 divided by 0.1 times 0.1 times 0.1 will actually equal 1,000 kilograms per meter cubed. And that actually is the density of fresh water. So that's a number you might want to kind of keep in mind, because we're going to be using that number quite a bit today in this video. All right. So this is another example problem. Things float or they don't float based upon density. And if the object is more dense than the liquid that it's in, it's going to sink. And if it's less dense, it will float. And the same principle is true with a submarine. Submarines rise up out of the water because basically they expel water from an internal chamber in their ship. Whereas if they want to sink, they actually have pumps that pull water into this internal chamber to make them more dense, causing them to sink. So it says fresh water has a density of 1,000 kilograms per meter cubed. Which of the following materials will float on water? Well, basically, you're looking for any material that is less than 1,000 kilograms per meter cubed. So as I go through these, would ice float? Absolutely. And that kind of makes sense if you ever have like a soda or something and you have ice in it, the ice is on top, right? Would magnesium float? Density of 1,740? No, it's more than 1,000. Would cork float? Yes, it would. Cork would float because it is less than 1,000 kilograms per meter cubed. Okay, and then glycerol would not float because it's more than 1,000. So it's just basically, is it more than 1,000 or less than 1,000? If it's less, it floats. If it's more, it sinks. So this leads us to our first discussion point here, which is buoyant force. What basically ended up happening was that it was discovered that when an object is submerged in a liquid, some of the object's weight is displaced by this buoyant force, and the buoyant force pushes up on the object. And so I don't know if you've ever tried lifting someone up in a pool. They feel considerably lighter if they're underwater, and the reason why is the water's helping you lift that person up. They provide a buoyant force. So buoyant force is exerted by all fluids, and not just water, so it can be any fluid, and it all depends on this formula down here on the bottom. The buoyant force equals the density of the fluid times the volume displaced, that's what the V is, the volume displaced of the water, times gravity. So that's going to be an important formula that we're going to be using in the next couple of example problems. So buoyant force is density of the fluid times the volume displaced of the object, and maybe I should add that in here, of the object, times gravity. All right. So Archimedes was actually the guy who discovered this, and basically that's why it's called his principles, because he was the one that kind of discovered this buoyant force, and his discovery is called Archimedes' principle, and as I mentioned in the previous slide, it's basically the weight of the fluid displaced is the buoyant force. Okay, so again, there's that formula that is kind of important to know. So let's do an example problem with buoyant force. It says, what is the buoyant force on a 0.3 meter cubed box which is fully submerged in fresh water? And then again, the density of fresh water is 1,000 kilograms per meter cubed. And so what you're going to be doing is you're going to be using Archimedes' principle. And Archimedes' principle is the buoyant force. So the buoyant force equals rho volume displaced times gravity, right? And I'm just going to start plugging numbers in to find out the buoyant force. So rho is 1,000 kilograms per meter cubed times the volume displaced, which is, so this box has a volume of this, and it's fully submerged. The box is under the water, so it's 0.3 meters cubed, times the gravity on Earth, which is 9.8 meters per second squared. And if you run those numbers through your calculator, I get a buoyant force of 2,940 newtons. All right. So basically what it's saying is this box is being pushed with an upward force of 2,940 newtons from this buoyant force. Okay. Here we have a little bit more of a challenging problem. So let me change my pen color here to, we'll say, I guess, yellow. So it says a steel cable holds a 120 kilogram shark tank 3 meters below the surface of salt water. If the volume of the water displaced by the shark tank is 0.13 meters, what is the tension in the cable? And then again, assume the density of salt water is 1,025 kilograms per meter cubed. The density of salt water is a little bit different than fresh water. So it's sometimes why they have saltwater pools at like fitness centers and stuff, because basically it helps people float better so they can swim through it easier. Anyway, that's neither here nor there. Anytime you have a physics problem, I highly recommend drawing a diagram, and in this case, a free body diagram. So if I draw the shark tank, here it is, we basically have three forces acting on this shark tank. We have the weight of gravity pulling down, right? And so I'm going to call that force of gravity, Fg. And then we have the buoyant force pushing up, helping fight against gravity, but that appears not to be enough. There is some tension in a cable. I'm just going to call that force of tension in the cable. Okay, so basically gravity is fighting the buoyant force and the tension in the cable. What you need to be able to figure out is, because it says the shark tank isn't like sinking downward or moving, you have to assume that it is stationary. And when it's stationary, it must mean that the net force, or F net, on this thing, this shark tank I should say, is 0. And so why that's important is because we can now say the tensional force and the buoyant force is equal to the force of gravity. Because there's no movement, they must cancel each other out. And so I can set these guys equal to one another. F tension equals, let's see if I can fix that. Force of buoyant, I'm going to make that a better T. Force tension plus the force of buoyancy equals the force of gravity. And I'm really sorry, that looks really messy there, but that's force of tension plus force of buoyancy equals the force of gravity. So I'm going to start kind of just plugging things in based upon what I know. So this force of gravity, how do you find the force of gravity? Well, that's just mass times gravity, mg. Mass times gravity. And that is equal to the force of tension, which is what we're trying to find out. So I'm just going to call that Ft. Plus the buoyant force, which we just learned was rho volume displaced, which is V, times gravity, which is G. Okay, so now I can just start to plug numbers in and start to solve this problem. So the mass of the shark tank we said was 120 kilograms, and gravity on Earth is 9.8 meters per second squared, equals the force of tension, which is what we're trying to solve for, plus the density of salt water, which is 1,025 kilograms. I'm running out of space, so I'm going to stop writing the units, but they're there. Please make sure you write those. Times the volume, which is 0.1, times the gravity, which is 9.8. Put a decimal point there. Okay, and so basically this is just a division problem. I'm going to take these two numbers, multiply them by each other, and then divide it by this chunk of numbers here to get my tensional force, which if you do that in your calculator, tensional force, let's see here, I have 171.5 newtons. Okay, and so again, this is a little bit harder problem, but if you can just kind of get that idea that this cage isn't moving, it really opens the door to being able to solve it. Okay, let's take a look at another buoyant force problem. It says a rectangular boat made out of concrete with a mass of 3,000 kilograms on a freshwater lake, which now has a density of 1,000 kilograms per meter cubed. If the bottom area of the boat is 6 meters squared, and I'm sorry I forgot to square this, this is 6 meters squared, not just M2, and this is cubed, M3. If the bottom area of the boat is 6 meters squared, how much of the boat is submerged? Okay, so again, I recommend kind of thinking about a drawing. It's not as important in this one as compared to the other one, but if you have a boat, what's pulling the boat down? Well, it's the force of gravity. And what's balancing the boat out? Well, it's the buoyant force. Okay, these two are in competition with one another. And clearly this boat is not sinking because it's saying that, you know, part of it's submerged, but not all of it, okay? So since there's no movement, there is no net force, F net equals 0, I can set these two equal to one another. So I have FB equals FG. And FB, as we know, is density times the volume displaced times gravity equals the force of gravity is M times G. All right. The problem is I don't know how much volume is displaced. That's part of what I want to figure out, right? Volume is partly what's missing. Well, what's the formula for volume? Volume equals length times width times height, right? Well, they tell us that the area of the boat is this. And area is actually really just these two figures here. That's area, right? Length times width is your area. So I can actually, in my problem, replace V with A times H. Okay, so if I rewrite this up over here so I have a little more space, I have density times area times height times gravity equals mg. Okay, and again, where did I get this AH from? Well, area is length times width, and then the height's just the third term, and that's actually what we're trying to find right here, is this height. Okay, so let's solve this bad boy. The density is 1,000, and I'm going to again skip units just because I'm going to run out of space. 1,000 times the area, which is 6 meters squared, times the height, which we don't know, times gravity, which is 9.8, equals a mass of 3,000 kilograms times the gravity, which is 9.8. And if you do that math, H should equal, let's see here, 0.5 meters. Right? That's how much of the boat is submerged. 0.5 meters of it is below the water. Okay. If you were to say put more stuff on the boat, it would probably be submerged more, right? Because the weight of the boat would have changed, so the boat goes down. If you take stuff off the boat or less people on the boat's height would rise. Okay, so now we're kind of switching gears here. We're talking about this thing called Bernoulli's principle. And Bernoulli's principle states that fluids moving at higher velocity lead to lower pressures, and fluids moving at lower velocity results in higher pressures. And that sounds kind of confusing, but a good example is if you think of a garden hose, and you've got a hose. Oh, I should change my pen color. You've got a hose, and then at the end you have that the spigot. Basically, what this principle is saying is that if you have this hose, and again, I wish I was a good drawer, and then towards the end you kind of have like this spigot, the velocity here is going to be higher at the end of the spigot, and the pressure is going to be lower compared to, say, over in this area. The velocity is going to be lower and the pressure will be higher. And that's all Bernoulli's principle basically says, is when you make the area smaller, the velocity increases, and when you make the velocity increase, the pressure must go down. Okay, so maybe let's take a look at some pictures, and this might kind of help make it more intuitive. Here we've got a nice pipe, right? And on the left-hand side here, you've got really high pressure, but the speed is slow. All right. As this pipe narrows down into this thin area, the pressure has to decrease, and when the pressure decreases, the speed increases, so you can move more fluid through that pipe. And then when you expand out again, now the pressure has increased, but the speed has decreased. And that's basically all Bernoulli's principle is. It also applies to partially how the planes get lift in terms of taking off. The top part of a plane's wing has a higher area than the bottom part, and so the wind has to move faster on top of the wing, and it causes lower pressure, less push, if you will. And so there's a force, an upward force, this direction because the pressure is higher here, and that causes the plane to go up partially. There's other things in play, but partially Bernoulli's principle explains how planes can fly. So this is Bernoulli's equation, and like, holy cow, don't let this scare you. It is really big, but it's not as bad as it appears. A lot of times you can cancel some of these terms out when you're solving a Bernoulli's problem, which I'm going to do one in just a second. So P1 is pressure 1, and then plus 1/2, and this is again rho, this is the density of the liquid, times the velocity squared, plus the density of the liquid times gravity times the height above the ground, equals the second pressure times rho times velocity squared times density times gravity times the height above the ground. And again, as I said, this looks horrible. It's really not that bad. We'll take a look at an example problem right now. So water sits in a large open jug at a height of 0.2 meters above the spigot. Okay, so take a look at this picture here. Here's the spigot right down here, and this water from the spigot is 0.2 meters above the spigot. With what velocity will the water leave the spigot when it's open? So what is the speed down here? What is V2? That's what I want to know. Okay, so we've got this equation here. Here's Bernoulli's equation, and there's a couple things that we can kind of think about. The pressure is referring to like the atmospheric pressure, the push down on this tub of water. And since we're on Earth, the atmospheric pressure is basically the same everywhere. And so this pressure, this atmospheric pressure, actually will cancel out because they're the same. The pressure down here at P2 is the same as the pressure up here at P1 because we're on Earth and the atmospheric pressure is exactly the same. So that term is gone. All right. Then here is V1. The rate at which this water drops compared to the speed that the water is leaving the spigot is going to be very slow. This water drop up here is going to be very slow compared to the speed that the water leaves the spigot. So this V1 we can assume is 0. And anything times 0 is just going to be 0. So we can actually cancel out this whole term here. It's gone. Okay. The second thing we can actually do that's kind of cool is this height. This initial height here, we can assume also is 0, and so we can actually cancel out this term, okay? Because anything times 0 is 0. So what we're left with in the end is rho g y1 equals 1/2 rho v2 squared. And you'll notice one other thing I can do actually mathematically is I can cancel out the density of water, right? Because I have P on both sides, or rho, I should say, I shouldn't call it P. So I can cancel that out too. And what I'm left with is gy equals 1/2 v squared. Okay, so what is that? Well, 9.8 times the height, which is 0.2 meters. Put the parentheses there. Equals 1/2 v2 squared. Okay. And in the end, what this becomes is v equals 2 times 9.8 times 0.2 with a square root over it. And if you do the math, v equals 1.98 meters per second. Again, this looks horrible, but it's really not that bad if you can start to kind of just work your way through it and figure out what you can cancel. This problem becomes a lot less, because I promise you we'll never use this problem where we have all the terms in it. That's beyond the scope of this course. So you can always be able to cancel things out. Alright, that takes care of today's video. We'll see you guys next time.